Hey everybody, welcome to video 9-3. This is where we're talking about properties of rectangles, rhombuses, and squares. And so we're going to explore that through, of course, our basic definition of rectangle here. We know that a rectangle has 4 right angles on this first page. I'm on page 447. But on the next page, we're going to talk about why it is that we can prove a couple of these properties of rectangles. So let's look at them. The properties of rectangles are the following. If a quadrilateral is a rectangle, then we can safely assume that it's also a parallelogram. So it's one of those subcategories of parallelograms. And then if a parallelogram is a rectangle, we also know that it's a parallelogram whose diagonals are congruent. Diagonals congruent. So in example 1 here we have a rectangle drawn. ABCD is a rectangle. And what we're being asked to prove is that it is also a parallelogram and that its diagonals are going to be congruent. So its diagonals, remember, connect opposite corners, so A to C and B to D. Now you'll notice what they've done is that they've transitioned this diagram here to pull apart overlapping triangles, ACD and BDC. So that's going to be important as we go through the proof here. So let's see what we can fill in as we go. First of all, statement 1, ABCD is a rectangle, is a given. Statement 2, A and C are right angles because of the definition of rectangle. Statement 3, A is congruent to C because all right angles are congruent. So statement 4 is where we get to B and D are right angles, and that is because we've been told that it is a rectangle. So that's the definition of rectangle there as well. And then of course B and D are congruent again because all right angles are congruent. After we know that ABCD is a parallelogram because of the definition of parallelogram, and specifically the definition part of parallelogram we're talking about is that opposite angles are congruent. And what we've proven here is that 2 pairs of opposite angles, A and C and B and D here, are congruent. So therefore, if it's a rectangle, it's also a parallelogram. So there's the first part of the proof there. Prove that it's a parallelogram. We've done that. Now what we need to prove is that AC is congruent to BD, that those diagonals are congruent. So what we're going to do as we're moving on in this proof here, I'll keep those diagrams visible for us. Next we're going to go to that AD is congruent to CB, and that is by working with the definition of a parallelogram whose opposite sides are congruent. So I'm going to go ahead and put those markings up here on the triangles separated diagram. And then DC is congruent to DC. That's just because of our reflexive property. It's a shared side there. And then D and C are right angles by the definition of rectangle. They all have 4 right angles. And so if D is congruent to C, because all right angles are congruent, then the next statement we can make is that these 2 triangles up here at the top, I hope you can see the side angle side proof coming out there. So we're going to have triangle ADC is congruent to triangle BCD, and that is by the side angle side triangle congruence theorem. So finally, what allows us to say that the second part, that the diagonals are the same, that AC is congruent to BD there, is because they are corresponding pieces. So corresponding parts of congruent figures are congruent. So that's the first proof, you guys. The next thing I want you to prove is, or to work on, is at the bottom of this page here, under the Your Turns, we're going to be finding each measure. Just a quick little hint here. Remember how we pulled apart the diagrams for the proof? What we're going to do is ask you to go ahead and think of these as two separate triangles as well, overlapping triangles here. And of course we know we've just proven that any of the diagonals of a rectangle are congruent. So notice what it's asking you for. For number 5, it tells you AD is 7.5 here and DC is 10, and they want you to find the diagonal going the other direction. Well, hopefully you can see, if I'm just highlighting really quickly, they gave me this, they gave me this, but if I'm trying to come across the other direction, that's the same as the diagonal coming across this way, as we know. So hopefully you can see that we are going to be using your Pythagorean theorem on these problems. So take a pause on the video right now and go see what you can do with number 5 and 6. Okay, explain 2. We're going to be proving that the diagonals of a rhombus are perpendicular. A rhombus is a quadrilateral, as we can see at the top here, that has 4 congruent sides, and that figure shows rhombus JKLM, as you see over here on the right. There are several properties of rhombuses that you need to know. First off, if it's a rhombus, it's always a parallelogram. Then, if it's also a rhombus, we know 2 things. Its diagonals are perpendicular, so they're going to intersect at right angles. And if a parallelogram is a rhombus, then each of its diagonals bisects a pair of opposite angles. Another way to state all this is that it has basically 2 lines of symmetry through the diagonals. So it can fold itself from left to right or from top to bottom. Keep that in mind. So in example 2 here, we're just going to fill in as we go. We know that it's a rhombus. What we're trying to prove is that this angle at the middle, at angle N, at point N here, is a right angle, that they're perpendicular. So, since JKLM is a rhombus, JM is of course congruent to the other side there, JK. And because JKLM is also a parallelogram, MN is congruent to KN because the definition of a parallelogram, it's the part where the diagonals bisect each other. So by the reflexive property next, we can say that JN is congruent to itself. So what we have here in this diagram, if we zoom in, what we've just marked is that, of course, we know JM and JK are the same, and we know that we've got this right here going on, that reflexive property, and we also know that because it's a parallelogram, it is bisecting its own diagonal there. So I hope at the top you can see, if we were to come back to our proof here, that the triangles are congruent by the side-side-side theorem. So once we know that the angles J and K and angle JNM are congruent by CPCTC. Then by the linear pair theorem, if those 2 angles on either side there are supplementary, then that means they add up to 180 degrees, their measures. And since the angles are congruent to each other, by substitution, the 2 measures are the same, or in other words, twice one measure equals 180. So therefore, at the end of this paragraph proof, the measure of angle JNK equals 90 degrees, and therefore we've proven what we set out to prove, which was that JL was congruent to MK. In your reflect next here, down the page, we want to know what can we say about the image of J in the proof after a reflection across MK. I hope you can see that that image is L. And then reflect number 8, what property about the diagonals of a rhombus is the same as a property of parallelograms? And then what special property do the diagonals of a rhombus have? Well, the thing that makes them the same, you guys, is that the diagonals will, in a rhombus, bisect each other. But additionally, the diagonals also, what makes them special in a rhombus is that they are perpendicular. And not only are they perpendicular, but they bisect the angles themselves. Remember that whole folding left to right and top to bottom thing that we talked about. All right, let's move on. Okay, on the next page, explain 3 here, we're going to be using the diagram of the rhombus that we're given to find each measure. So for part A, what we're going to do is we are going to find the measure of xy. So that's this right here at the bottom. Now, of course, we know it's a parallelogram, so xy is going to be congruent to VW. And because it's a rhombus, VW is going to be the same as WX. So that's how we're going through here. All sides of a rhombus are congruent, so specifically VW and WX are congruent, and we're going to set up that algebraic equation. Then we're going to solve for m, so a couple steps in between here. We get 2m when we subtract 4m, and then add 12, and we get 16, and then of course m equals 8. But we're not done once we found the variable. We need to make sure we substitute that variable back into the length for VW. So we have 6 times 8 minus 12 is going to give us our 36 for our answer. And then if VW is 36, then all the sides are 36. So we have our answer finally that XY is 36. Okay, now we're going to do the same for part B. For angle YVW, that's this outside angle here, what we want to do is we want to figure out that the diagonals of a rhombus are perpendicular. You can put the perpendicular symbol there. So angle WZX is a right angle, which is 90. And then since WZX we're given is 3n squared minus 0.75, then what I can say is that that 3n squared minus 0.75 value has to be equal to the 90-degree angle that I know that it is. And when I solve for n there, a couple steps off to the right, we get 3n squared is going to equal 90.75. And if we divide there, we get n squared equals 30.25. And if we take the square root, we get that n is 5.5. And then finally, we're going to substitute that value of n that we just found in to find the measure of angle WVZ. So that's going to be 9 times 5.5, and then add 4 to it. Again, WVZ, if we go back up to the diagram, WVZ is here. 9 times the n value plus 4, and a little bit of math on that gives us 53.5. Now once we know that angle, remember our goal here is to find YVW. And YVW is twice the angle that we just found, WVZ. And so if we substitute 53.5 that we know for the measure of angle WVZ, that's 2 times 53.5, and then we get our 107. Okay, in the your turns, you're going to go with those values that you were just given there to find the other measures of the angles in the rhombus, and pick up from there with the ideas of the diagonals doing what they do in the rhombus, and we should be all set. A reminder one more time, make sure that you're going to our webpage to link to the Your Turn answers so that tomorrow you can jump in with the evaluate and be ready to go. See you later.